Thanks, Don, for getting me to come down for the visit. I had a really nice drive over through the Gila National Forest to get here yesterday. And as you'll see from some of the pictures I showed today from forests in the Northeast, it's really a pretty different landscape from what I'm used to. I grew up in Toronto, and never thought I would really be so far from the, living so far from the Canadian border, but here I am. So I'm going to come back to this photo, I'm going to come back to this picture, but it's more than 45 years since Apollo 17 astronauts took this picture of our planet Earth from space, and it's one of the few human-recorded images that shows an almost fully illuminated Earth disk. I think that's great. So Apollo 17 was the last manned lunar mission, and in the decades since, no human has been back at this sort of point in space far enough from Earth to take a similar picture of our planet. And I just wanted to show this picture to get you thinking about the power of photographs, or especially photographs as a permanent record of a particular scene at a particular point in time. And so today I'm going to talk about how with the PhenoCam Network we're using imagery from digital cameras to track vegetation phenology in a diverse array of ecosystem types. And I'm going to talk about what this is telling us about connections between phenology, ecosystem processes, and climate change. And I want to acknowledge the contributions of my collaborators to this work and our funding from various federal agencies. And last but not least, I want to thank our many site collaborators, including people like Don, for their support of PhenoCam, because this project, as you'll see, is really a collaborative effort, and it wouldn't have happened without those people on the ground at field sites. So when I was coming in, I heard people joking about phrenology versus phenology. Of course, I have to start with this slide just to clarify. I want to distinguish between phrenology, which is sort of the study of bumps on the head and all that. The lecture for that, I think, is on the other side of campus.
Sorry, wrong version.
Yeah, okay. And phenology, which is really the study of seasonality and seasonal rhythms. And the images shown here all give classic examples of different types of phenology, from spring emergence and flowering by plants, insect metamorphoses, the migrations of birds and mammals, and then also things in the autumn, like the ripening of crops, autumn leaf colors, and fall senescence. And the point I sort of want to make is that phenology is really all around us all the time. As we cycle through the seasons, new phenological events are constantly occurring. And so phenology is inherently of interest to ecologists because it represents this point of intersection between organisms and their growth environment. But it's also of interest to the general public. People tend to just be inherently fascinated by the passing of the seasons and the way in which symbols of that passing are manifest. So, you know, people get excited about seeing the first robin in spring or the first sign of colors in fall. And so phenology has been lyrically referred to as the pulse of our planet and the rhythm of the seasons. And this rhythm is nicely captured by this video, which is derived from NASA remote sensing. And it shows the annual cycles of vegetation development and senescence around the globe. And you really get a sense of that pulsing and rhythm. Okay, but so what? Is there a deeper reason we might be interested in phenology? This handsome gentleman has been referred to as the father of phenology in America. Does anyone in the room know who this is?
It's thorough, isn't it?
It is, and I have found that few people outside of New England actually recognize this as Henry David Thoreau. Is that what you were going to say, Don? Okay, good one. I saw someone do a talk in Vienna once at the European Geosciences Union conference. The whole thing was about Thoreau and phenology, and the Europeans in the room were like, "Who is that guy? I've never heard of him before." So Thoreau famously kept meticulous phenological records while living at Walden Pond, and he wrote very poetically about phenology, as you see here. And it was work by people like Thoreau and others, sort of these gentleman farmer types with lots of time on their hands, that led to the perception that phenology as a discipline wasn't real science. Now, Aldo Leopold also kept very detailed phenological notes, and his objective was to assemble a calendar of the seasons, illustrated here, from which you could see how different phenological events related to each other and how the sort of the rhythm of the seasons would unfold in a typical year. And Leopold believed that a deeper understanding of phenology could help one to find order and meaning in nature. So for a long time, the collection of phenological data by people like Thoreau and Leopold and others led to this perception that phenology as a discipline was really just an obscure branch of natural history. And the goal of phenology, the idea that the goal of phenology was just to find order in nature. But over the last couple of decades, there's really been a surge of interest in phenology and these seasonal rhythms of plants and animals. And it's increasingly recognized as an essential component of cutting-edge global change science. And coming back to this picture, this is the iconic blue marble photograph. And the Earth has really changed a lot since Apollo 17 astronauts took this picture, December 7, 1972. So we're seeing changes in the Earth's atmosphere, rising concentrations of greenhouse gases, carbon dioxide, and methane. And these atmospheric changes are then driving recent climate change. And this includes rising temperatures and altered precipitation regimes, which are then affecting how ecosystems work. And specifically, phenology is really getting a lot of attention these days because it is shown to be a leading indicator of the biological effects of climate change. So just as an example, there's substantial evidence for the advancement of spring phenological events, such as leaf out and flowering, by about 2 to 5 days per decade since the 1970s. And similarly, there's many examples in the published literature of autumn phenological events, such as leaf coloration and leaf drop occurring later. And these studies show really conclusively that the growing season is changing. It's being extended at both ends. And in addition to being reported in the scientific literature, these studies have also been widely covered in the popular press. And this goes back to the idea that as humans, we're just inherently fascinated by the passing of the seasons. And I think one reason that studies related to phenology get covered is that it's much more accessible to the general public to say, oh, well, the growing season is 10 days longer than it was when your parents were your age, or 10 days shorter than it is now. It is now 10 days longer than it was when your parents were your age, than to say there's been an X fraction of a degree change in temperature over that time. It's a way of expressing climate change in a way that's accessible to people. And then in the, now 11 years ago, but in the IPCC's fourth assessment report, they concluded that phenology is perhaps the simplest process in which to track changes in the ecology of species in response to climate change. So just to get the idea that this is really a growing field of great importance. So shifts in phenology are important for a number of reasons, and these reasons cut across a wide range of scientific disciplines. So phenology matters for ecological interactions, matters for ecosystem services and climate system feedbacks. And it's also really important to human society. So there's public health issues related to allergens and disease vectors. It matters for agriculture, planting and irrigation schedules, pollination, and so on. And it's also important for tourism. And this is things like wildlife viewing, bird watching, wildflowers, leaf peeping, hunting, all sorts of things. So just some examples of the different disciplines in which these phenological shifts are relevant. Okay, so with that introduction, I'm now going to talk about the specifics of what we're doing with the PhenoCam Network and how this is informing our understanding of the impacts of climate change on phenology. So the PhenoCam Network does what we refer to as near-surface remote sensing of vegetation phenology. We're using imagery from network digital cameras. This is what one of the cameras looks like. Of course, it's not really that big. They're about the size of my fist. We're using that imagery to continuously monitor plant canopies. Those images are recorded every 30 minutes from sunrise to sunset, 7 days a week, 365 days a year. These guys are out there working around the clock for us. One thing that is very appealing to me about this is that the scale of observations is comparable to that of tower-based flux measurements, stand-level forest inventories, and small watershed measurements. So it gives us a really direct link between what's happening on the ground at sort of the level of individual organisms integrated up to canopy scale, and then it allows us to relate that to what's seen at a coarser spatial and temporal scale and what's seen by satellite sensors. And this is a view from where we first put up a camera in 2005. This is the Bartlett Experimental Forest in New Hampshire, and it's as I was saying, kind of a different ecosystem from anything around here. I'm just going to run through a year of pictures now from Harvard Forest to sort of show you this rhythm of the seasons unfolding there, and as seen by PhenoCam. So this is a picture in late April. The snows have melted, but the canopy is still pretty much in a dormant state here. The dominant species, you can see these evergreen white pines. They are the tallest trees in the forest, but the really dominant, most abundant trees are red oak and red maple. So the deciduous trees are in a dormant state until about the first week of May, second week of May, and the leaves are just beginning to emerge, and there's this beautiful sort of emerald green color. Over the next 6 weeks, the foliage is maturing, the canopy becomes a much darker green, the leaves are elongating and thickening. The leaf area index of the canopy is peaking by about the end of June. We move into August, and there's a little bit of yellowing of the canopy as a whole, and you can see some individual trees are starting to show stronger autumn colors. We fast forward into October, and the canopy in mid-October is this brilliant mix of oranges, browns, golds that's really typical of these maple and oak-dominated forests in central and southern New England. This won't last long, though, because by December, the canopy is again bare, all those leaves have been dropped, and we're back in this state of dormancy that won't be broken until the following spring. So, the camera images give us a permanent record that we can look at any point. We can look at the images and visually estimate when the leaves started to emerge in spring, when they began to change color in autumn. As Don mentioned, our original goal was just to have pictures that we could use for talks about our flux tower measurements. You know, this is what the forest looks like from the top of the canopy. But it turns out we can also get quantitative imagery extracted directly from, quantitative data directly extracted from that imagery. And the reason for this is that digital camera images use what's known as the red, green, blue additive color model, which says that we can reproduce any color as perceived by the human eye through some combination of those three primary colors, red, green, and blue. And what that means is we can take a picture, like this one from Harvard Forest, we can split it into the red, green, and blue components, the different color channels. We can then define a particular region of interest within the image that we want to study. And then we can quantify for each of those three color channels the brightness or intensity of the pixels within that image for that region. And that gives us this quantitative measure of leaf color, or of canopy color for that region. And we can take that red, green, and blue numeric triplet and convert it to something like a greenness index, which is just basically the relative brightness of the green channel relative to the sum of the red, green, and blue channels. And when we do that for multiple years of imagery for Harvard Forest, this is what you get, a very clear representation of the seasonality of the vegetation of the forest. So in wintertime, greenness is low. As those leaves emerge in spring and expand, the greenness rapidly increases. As the foliage matures over the summer, that greenness kind of drops off a little bit over time. Then there's a rapid drop in greenness in the autumn as the leaves change color and then as they are shed. And we can extract, numerically, we can extract transition dates from these time series based on changes in the shape of the curves. And the transition dates we extract line up very nicely with dates of bud burst, canopy maturity, leaf coloration, and leaf drop as observed on the ground. By a human observer. So the point is that the PhenoCams are providing data that are consistent with ground observations, but automatically and at a much higher temporal resolution. And then uniquely, because these are images, we can selectively analyze whatever part of the image we're most interested in, whether it's just looking at the trees in the foreground here and ignoring what's going on in the background and in the sky, or whether we want to break it up and look at the crowns of individual trees as I showed here. So the same approach is also able to track changes in the greenness of other types of vegetation. So going back to 2010, we've had a camera set up looking at a mixed C3, C4 grassland at about 3,000 feet on the western flanks of Mauna Kea on the Big Island in Hawaii. And here seasonality is driven by the timing and magnitude of precipitation events. And you can see across the bottom here, well actually you can't see the numbers here, because, well, this is one year here, and that's 1 year, and that's 1 year. So this is 3 years, and you can see that in some years there's sort of 1 or 2 green ups, and then here we got 3 green ups and downs. And basically there's a lot, there's not just a single, the seasonal rhythms here are much more variable than they are at places like Harvard Forest. But the point is, we can use the camera images. You can see here, hopefully this isn't giving anyone a seizure with the flickering and stuff. You can see the vegetation greening up and then turning brown, greening up and turning brown, and that's then represented on the bottom here. Okay, what about evergreen vegetation? It turns out that evergreen forests, some evergreen forests are a lot more seasonal than others, and this appears to be driven by the extent and duration of cold temperatures that are received. So this is Niwot Ridge, Colorado. This is a high elevation conifer forest dominated by spruce, fir, and pine, and we see very strong seasonality in the greenness here. A very surprisingly clear signal, given that this is an evergreen forest. And chemical analyses have shown us that these changes in canopy level greenness are related to changes in pigmentation at the leaf level, so the abundance of chlorophylls and carotenoids, and not by the production and senescence, production of new foliage and senescence of old foliage. It's really being driven by changes in leaves that are already there. And this just shows you, left is July, and very green, right is January, and much more of a red-brown color to the canopy. And that's just to show you that these, our greenness metric really is picking up on, you can visually see here too. In other evergreen ecosystems, the seasonal changes are much less pronounced. And so this is 2 years of data from a camera in Volcano National Park, again on the Big Island of Hawaii. The y-axis range here is the same as for the Niwot data shown above. And you can see that there are some wiggles in the greenness, but they are much less pronounced, and the amplitude is much smaller than at Niwot. This is a site that is warm year-round. And thanks to collaborators such as Don and Scott Collins, Marcy Litvak, and others, we now have a nice sampling of arid sites in New Mexico, and this is really helping us to fill in our representation of diverse climate regimes and ecosystem types. So just showing some pictures from the Sevietta grassland site and Sevietta shrub site. The grasslands and shrubs, not surprisingly, are doing a little different things, and then a Jornada site down here. So the first PhenoCam was installed at Bartlett Experimental Forest in the White Mountains of New Hampshire about a dozen years ago in the fall of 2005. By 2008, I had a really small amount of funding to start a small regional network focused on the forests of northeastern United States and adjacent Canada. But over the last 10 years, the PhenoCam Network has really blossomed. I hate to use that pun, but it's true. It has blossomed into what is really a continental scale phenological observatory. So we now have over 400 cameras contributing data to the PhenoCam Dataset. Most of these are located within the United States. We have cameras across the country, from Hawaii to Maine, and from Alaska to Arizona to Florida. We also have some cameras in Canada and Panama and a handful of countries in Europe. And the imagery and data are all publicly available through our project webpage in pretty much near real time. And this is the URL here. If you just Google PhenoCam, you'll find that. And this is just showing sample images from a range of different ecosystem types: grasslands and prairie, savanna and shrubland, deciduous and evergreen forests, as well as agricultural crops. And we're really increasing our representation of ag sites through Don's efforts. Our ultimate goal really is to have a comprehensive sampling of all the diverse ecosystem types in North America. And so I want to talk about some of the things we're learning from the data. So temperate deciduous forests tend to be highly diverse, but often we don't have the detailed information on species composition, species-specific responses of phenology to environmental factors and so on, to be able to account for this diversity in simulation models. And so the land surface schemes that are embedded in the really complex Earth system models of the sort that are used to make projections about future climate change use phenology models that are very simple and that are applied at the level of plant functional types. So for all deciduous broadleaf forests worldwide, there's a single model formulation and a single set of parameters. And some of our previous work has shown just how poorly these models actually tend to perform, either because the model structure or the model parameters are not appropriate for all locations. And we set out to investigate whether we could improve on those kinds of models. First of all, we wanted to find out how much better we could do if we explicitly accounted for differences among species in the phenological response to environmental factors. And this is work that was led by Eli Melas here when he was working on his PhD at Boston University. And we compared two different modeling approaches. First of all, we came up with a set of species-specific models. These were calibrated USA National Phenology Network ground observations of leaf emergence, and then upscaled from the species level to the canopy level using forest inventory data. And we compared that with a species-ignorant model, which was derived using canopy scale PhenoCam observations from across a range of sites. And this is just showing on the left, this map shows the locations of the USA NPN data, the smaller dots colored according to species, and the PhenoCam sites, the larger yellow dots that we used for our modeling. And on the right, just in case you're as unfamiliar with the Northeast as I am with the Southwest, this is just showing the extent of the eastern deciduous forest. And so what we did was we used the two different types of data to constrain about a dozen different phenological models of varying complexity. And these models have different model structures that combine factors such as day length, or photoperiod, cool temperatures or chilling, and warm temperatures or forcing in different ways that have been hypothesized to govern these springtime phenological transitions. And we then selected the best model using a Cocky's information criterion and performed independent validation against start of spring dates derived from MODIS satellite remote sensing. We did the validation across the entire eastern deciduous forest. So 12 years of MODIS data from 2001 to 2012 were used for the model validation. And these figures just show the root mean squared error between the start of spring date from MODIS and the model predicted bud burst dates. With cooler colors over here indicating better agreement between model and data, and the warmer colors indicating progressively worse agreement. And you can see that each modeling approach is doing better in some areas and worse in others. So the NPN model is doing poorly in the Ozarks. Neither model is doing particularly well here at the higher elevations in the Appalachians. The PhenoCam model is doing fairly poorly down here in the deep south. But overall, we found, for both models, we found a low bias and median root mean squared error of about 5 days for both models. And while previous studies have failed to develop models that generalize well in time and space, here we show that by using PhenoCam data from a wide range of sites, we are able to parameterize a very simple model that is not species specific, that does generalize well and is easily applied across a wide geographic area because you don't need that species information. So our next step, we took the model that Eli developed in that paper, the simple PhenoCam model, and we put it into CLM, the community land model, as a replacement for CLM's standard winter deciduous phenology submodel. And this is work that was led by my former postdoc Min Chen. It was published about 18 months ago in Global Change Biology. Here, the old model is the existing model in CLM, and the new model is Eli's PhenoCam, species-ignorant PhenoCam model. And in terms of model predictions, you can see that both models predict similar geographic patterns. Earlier green up, here the greens are earlier green up and the reds are later green up, and you get similar patterns of earlier green up at low latitudes and later green up at high latitudes. If you look across all deciduous forest grid cells in the northern hemisphere, we get a similar mean date of spring bud burst of about May 1st for both models. But if you sort of start to really dig in, you will see that the differences between the models are highest at high and low latitudes. They're more in agreement at sort of the mid-latitudes. So we did a similar validation of the model predictions against MODIS data, this time for the entire deciduous forest worldwide instead of just the eastern deciduous forest. The old model had a root mean squared error of about 7 days. The new model cut that in half to just 4 days. And this is really largely because of areas for which the old model had particularly poor performance, including the southeastern United States, Eastern Europe, and Southeast Asia. And the new model did much better across those regions. So we then ran both models to 2100 using climate projections, again for all temperate deciduous forests worldwide. And what's sort of interesting, this is here the coloration shows that the mean change in bud burst date from between 2090 versus the decade of the 2090s versus the 2010s. And areas that are shown in red are projected to be greening up later than they are now. Areas that are green are going to green up earlier. What's interesting is that the existing model predicts relatively little change in spring bud burst for most of the globe. Although some regions, generally warmer, more southerly forests, are actually predicted to have later bud burst date by the end of the century than they do right now. And I just want to point out that these trends are inconsistent with pretty much every study that's been published looking at changes in phenology over the last few decades. By comparison, the new model predicts a much stronger advancement over the coming century, with the trends being strongest at the higher latitudes, as these areas are the areas that are expected to warm most in the future. Earlier I talked about the global mean bud burst date. They're about the same under current climate, but as we run the models forward, you see that around 2040 that they really are starting to diverge and not overlap at all, and by the end of the century, they're just getting farther and farther apart. So the old model predicts virtually no change in spring bud burst date by the end of the century. The new model predicts a mean advancement of about 10 days. This is globally average, so some areas are more than that and some are less, but about 10 days overall by the end of the century. This is being shown for the RCP 8.5 climate scenario, which is a higher CO2 future and more warming, with a RCP 4.5 scenario, which has less warming. The future change is cut about in half. Now, because the community land model fully simulates ecosystem processes on the land surface, we could compare CLM runs using the old phenology model with CLM runs using the new phenology model to look at how these shifts in phenology driven by climate change would affect carbon and water recycling. And what this analysis shows is that earlier bud burst is projected to lead to increased forest growth, more productivity, but also increased evapotranspiration or water use. And this is going to result in drier soils and reduced runoff for downstream uses. So there's some trade-offs there between the carbon and water. So compared to the standard CLM phenology model, the new model predicts a strong advancement of bud burst dates across the northern hemisphere temperate deciduous forest. These advances in spring bud burst then influence ecosystem processes related to carbon and water. And overall, although these effects are seen globally, they are stronger at higher latitudes. Okay, so I'm going to change gears a little bit. We've been also looking at how future climate change will impact grassland phenology and productivity, again using PhenoCam data for model development. So globally, the grassland biome covers about 20% of the Earth's land surface area. And in North America, grasslands consisting of short grass, mixed grass, and tall grass prairie cover about 15% of the continent. This is an ecologically and also economically important biome. And this is work that was led by my former postdoc, Koen Hufkens. So across the current extent of grasslands in North America, which here we're defining based on MODIS satellite remote sensing, I'm showing 10 different climate models here on the left. And they are projecting that by the end of the century, it's going to be pretty much warmer everywhere across the extent of grasslands. And so this is looking at shifts in temperature over the next 100 years. When you look at shifts in precipitation, the models are a little bit more variable, but there's sort of a general consensus of it's going to probably be a little bit wetter in the north and a little bit drier in the southern extent of grasslands. And so over the coming century, increases in temperature with relatively minor changes in precipitation inputs are projected to cause an increase in what's termed the aridity index, which is basically the ratio of mean annual precipitation to mean annual potential evapotranspiration. We're going to see an increase in aridity across the current, across the range that is currently dominated by grasslands in North America. And sort of the question motivating this study was, how are these changes in temperature, precipitation, and then aridity, how do those then affect grassland phenology and productivity? And we used a model-based approach to look at how these environmental factors would interact in the future. And our model couples plant growth to soil hydrology in a way that is designed to capture the pulse response vegetation dynamics which really characterize these grassland ecosystems. And this is just showing the overall model structure. We're using temperature, solar radiation, and precipitation to drive the model. We're tracking two model states, tracking vegetation cover and soil water. And at each time step, we're simulating the flows of carbon in terms of the growth and senescence of vegetation, and flows of water in terms of evapotranspiration and runoff. And you can see from the way I've illustrated the model structure that there are feedbacks between carbon processes and water processes that are explicitly represented by the model. So growth and senescence are influenced by soil water, doom and doom, and then evapotranspiration is influenced by vegetation cover. And so to calibrate the model parameters, we used canopy greenness measures from PhenoCam as a proxy for vegetation fractional cover. And we used over 30 site years of data from 14 different sites across the network to train the model parameters. And we then evaluated the model parameters using a one-out cross-validation approach. And then once we were convinced that the model was working pretty well, we estimated a single set of parameters that we applied across all ecosystem types. And this is just showing the cross-validation for a C3, C4 grassland site in Oklahoma. Seasonal changes in greenness from the camera are shown by the dots. Seasonal changes as predicted by the model are shown with the red line, and blue is just showing the precipitation inputs.
Where in Oklahoma?
It's a site near Norman.
Okay.
And this is then just taking those two times, the modeled and predicted time series, and showing sort of their correlation in time. And basically the model is doing a pretty good job of capturing these seasonal dynamics. And so what we did was then took the model and ran it forward for 10-kilometer grid cells to the year 2100, using as model drivers the 10 climate models that I showed at the beginning of this section. And really the key takeaway message is that we're going to see, an overall increase in productivity of about 10 to 20% across the North American grassland biome. And you can see here, darker greens are larger increases in productivity, and reds are decreases in productivity. You see the response is stronger in the north, where we are projecting that accompanying those increases in temperature, we'd probably see a little bit of an increase in precipitation, which is going to help offset that aridity change. And also in the south, the increase in productivity is a little bit weaker. Here, the shading up here is indicating areas of statistically significant increases in productivity when you look across the 10 different climate models. And I will say that the differences that we see between models, between different climate models, are really largely driven by those changes in precipitation, how different models, projections that different climate models make about future precipitation. Now, one of the interesting things to emerge from this modeling was that we're predicting that grasslands are going to respond to future climate change by shifting their seasons. So this figure here is just showing the difference, the change in the seasonality of vegetation fractional cover between 2010 and 2100. So the difference between the season cycle in those 2 years, with positive values indicating more cover at that time in the future. And generally what we're seeing is earlier onset of vegetation activity in the spring and delayed senescence of the vegetation in the fall. Those are sort of increasing productivity in the shoulder seasons. And then we're seeing some effects of summer drought, kind of reducing fractional cover and reducing productivity in the summertime. And across this area shown in dark green, those spring and autumn increases more than offset that summertime decrease, so there's a net increase in productivity across that area. And in the more southerly grassland areas, what we see is more like this, where there's a decent increase in spring, a smaller increase in autumn, and that is more completely offset by the summertime reductions due to drought. So big increase in productivity in the north, smaller or no increase in the south. And so the take-home message of this study is in the title of the paper, that the productivity of North American grasslands is increased under these future climate scenarios despite rising aridity. And we're projecting that earlier spring and delayed senescence more than compensate for summer drought effects, at least at the biome kind of scale, resulting in overall increased productivity. But we expect that these changes in seasonality will present some new management challenges related to grazing, planting and harvest dates, irrigation, and so forth. And it's pretty clear that these shifts in phenology and growth will influence key ecosystem services that actually do have real economic value to human societies. Okay, finally I just want to talk about how we're using PhenoCams to track vegetation phenology in an ecosystem warming experiment. So we're partnering with scientists from the Department of Energy's Oak Ridge National Lab, who've set up what is called the spruce experiment here, spruce and peatland responses under changing environments. This is a massive experiment being done in a black spruce sphagnum bog forest in the north central United States. This is a 10-year experiment. These chambers, there are 10 of them. They are about 8 or 10 meters high and 12 meters across, and they are being used to apply a range of carbon dioxide and temperature treatments to mature and intact patches of this peat bog forest ecosystem. And this just shows the experiment from the air. You can see here the evergreen vegetation in the low-lying bog. These are the experimental chambers, and the bog is surrounded by deciduous forest on the uplands. And overall, the experimental design aims to simulate environmental conditions that will likely be experienced in the latter half of this century. So there's 10 chambers in total, 5 different levels of warming, from ambient to +9 degrees Celsius. And then there's 2 levels of carbon dioxide. There's ambient CO2 at 400 parts per million and elevated CO2 at 800 parts per million. And the warming was turned on in August 2015, so we're going into the 3rd year of warming. And the CO2 was turned on in June 2016, so we're headed to the 4th year of warming and the 3rd year of CO2 enrichment. So we installed digital cameras, or these PhenoCams, in each chamber in August 2015, right at the time the warming was being turned on. The cameras are mounted on the south side of each chamber in a standardized position across all chambers at 6 meters high, so we're looking down and out across the vegetation. And sort of following the standard PhenoCam protocol, the images are recorded every half hour and they're posted in near real time to our project webpage. So just, again, coming back to the idea that these images give us a permanent record of what things look like. What I think is really cool is that we're going to be able to watch the experiment unfold over its 10 years, and if there's anything we want to go back and see, well, what are the events that led up to this tree dying or whatever, we'll be able to sort of have that historic perspective. You can see the effectiveness of the treatments. This is inside an unheated enclosure. It's on New Year's Day. It was about -5 degrees inside this chamber. There's snow on the ground. And this is inside chamber 17, which is one of the +9 plots. +9 is sort of similar to moving from Grand Rapids, Minnesota, which is just south of the research site, down to Tulsa, Oklahoma. So just to put that in perspective, I think it's 1,100 kilometers shift south there. What it means is that in the summertime, sometimes these chambers are getting to be 40 degrees Celsius, which is really kind of surprising. But anyway, this is on the same day. It was about +5 degrees inside this chamber. There's no snow, and you can just sort of see the difference in environment that's being imposed here. We're interested in using the camera data to track how the phenology of different organisms inside these chambers are affected by the warming, and also now the CO2 has been turned on by the CO2 treatments, and we've got 3 different competing hypotheses. So if temperature, if phenological transitions are controlled strictly by temperature, there should be a really strong and direct relationship between the chamber air temperature, so which is on this axis, the colder plots here and warmer plots here, and the phenological transition date. So, obviously, if this is kind of set up for autumn, it would be the other direction for spring, but cooler temperatures earlier, warmer temperatures later. In spring, it would be cooler temperatures later and warmer temperatures earlier. I think I'm confusing things, but it's also been suggested that some phenological events, particularly autumn phenological events, are controlled more by photoperiod or day length. And if that's the case, then these temperature treatments shouldn't cause any shift in phenology because basically the day length is the same in every chamber. And so if that's the case, if photoperiod is the driving factor, then the response to these warming treatments will be flat, as I showed here. It's also been suggested that temperature and photoperiod may kind of interact, and so that ultimately photoperiod limits the temperature response. The idea being here that due to evolutionary history, plants use photoperiod as a cue, and they know that no matter how warm it is, they still shouldn't be putting out their new leaves when the days are too short. And so what we might see is that there is a temperature response up to a certain point at this start threshold, and then beyond that photoperiod kicks in and limits the phenological advancement. And so I'm going to refer to this as the breakpoint model. We're looking for evidence of that threshold. So this is a view inside chamber 6. This is an ambient temperature treatment plot. And what I just want to show here is how we subdivide images like this into 3 different vegetation types. So we are separately studying the responses of larch, the deciduous conifer, black spruce, evergreen conifer, and then we're also looking at this mixed shrub layer on the ground, which is dominated by woody shrubs, leatherleaf, and Labrador tea. Yeah, did you have a question?
Yeah, the camera temperature is 44.5.
The cameras themselves actually generate a fair amount of heat. And that's actually a good thing because, I mean, it's just like from the internal electronics and stuff, but what that means is that we rarely have problems with condensation and frosting up that last very long because there's that gradient of higher temperature and lower humidity inside the camera housing. So it's actually, yeah, it's a good thing.
But that's not just the internal temperature.
No, that's the temperature of the electronics inside the. And actually, though, it does get about 10 degrees warmer inside the heated chambers, which is kind of interesting. But that does just bring up one point, though. You can see within each chamber just how much other stuff is. This experiment was not set up just for us. There's a whole range of other measurements being made. There's, I think, something like 8 different temperature sensors doing air temperature with inside the plot. There's peak temperatures at different depths. There's humidity and so on. It's a very sophisticated monitoring program, and we're just a small part of that. And so this is just showing for the first year of the experiment for autumn senescence dates and spring green updates derived from the camera imagery. For the larch in this column, the spruce in this column, and the shrub layer here, we're seeing autumn senescence is delayed by warming at a rate of about 3 days per 1 degree warming treatment. And also, we're seeing that spring green up is advanced by warming at a rate of about 2 days per 1 degree treatment. And together, what this means is that between the control chambers and the +9 chambers, there's more than about 6 weeks difference in the length of the active season between those two chambers. So these responses might not, 3 days per degree may not seem like a whole lot, but once you multiply that by the 9 degree treatment range, it really does add up. In general, we're finding that the response to temperature is significantly different from 0 and is generally linear. And so this, first of all, allows us to reject that strictly photoperiod model. It also doesn't give us much support for the breakpoint model, where photoperiod is predicted to limit future phenological responses. And in fact, only for one of these 6 data sets shown here could we identify a breakpoint that actually improved the model fit, and that was for the larch in spring. You can see maybe a little bit of flattening off there, but when we look at Akaki's information criterion, it again tells us that the simpler linear model, which is what I'm illustrating here, is better. So there may be a little bit of evidence that once you get to pretty warm temperatures, things will flatten out, but that evidence is pretty weak so far. So the camera results are supported by ground observations, not only on the 2 tree species, the larch and the spruce, but also on the shrub, herb, and sedge species that are shown here. So we're seeing earlier shoot elongation, earlier leaf growth, earlier flowering, and earlier seed formation. All these trends were highly significant and in the expected direction, with the mean rate of advancement of about 3 days per degree of warming. And again, there's little or no support for the breakpoint model. So the ground observations are consistent with the camera observations. Now, one last thing is, we had an extreme weather event in the spring of April 2016, so this was within the first year of the warming treatments being turned on. And this extreme weather event showed very dramatically how the warming treatments are triggering physiological changes that are not visually obvious. Specifically, what they're doing is, in addition to causing earlier green up, they're also advancing the timing of dehardening and loss of winter frost hardiness, and then this is enhancing the likelihood of frost damage in early spring. And so what happened was we had this really warm month in March, and that was followed by extreme cold on the morning of April 9th. And so through April 8th, the warmest chambers, the 2+9 chambers, had accumulated 8 times as many degree days as had been accumulated outside of any of the treated chambers. In these 2 chambers, it had been more than a month since the temperature dropped below 2.5 degrees Celsius, whereas outside the chambers, this was happening on a very regular basis. The night of April 8th, 9th, there was this blast of Arctic air. The temperatures outside of the chambers dropped to more than 15 degrees Celsius below 0. This was near record temperatures for the date and for the region. And even within the +9 plots, it dropped well below freezing, to below 4 degrees Celsius inside chamber 17 and -3 inside chamber 10. And what was kind of interesting was that black spruce, particularly in plot 17, suffered very severe and almost immediate frost damage, which we could then pick up in the camera images. So this is the morning of April 9th, well, noon on April 9th, so it's probably like 7 hours after those temperatures have hit their absolute minimum. And at first it doesn't look like anything is obviously wrong, but 10 days later, you can see how the tree in the middle goes from this tree here, nice and green, boom. Turns, sort of looks like your Christmas tree after you've gone away for 2 weeks after Christmas and left it inside the house without water. And there's some damage to the larch. This is a larch down here. They had just started to put out their new flush when that frost event happened. They dropped, a lot of their that juvenile foliage turned brown and was dropped, and then they put out a second flush. The spruce, over the following month, lost most of these brown needles, but then their buds put out a normal flush. So the spruce would generally flush probably in late May or mid-June, and these guys sort of flushed more or less on time. But by that point, they'd already lost 90% of their foliage. What was interesting was that in the other chambers, so there was some damage in the 7-degree warming chambers. The chambers that were warmed less suffered no damage at all, even though they got to much colder temperatures. And so what this means is that those chambers were still retaining sufficient hardiness to tolerate those freezing temperatures. And it was only in the warmest temperatures that hardiness had been lost. And this is just showing how severe that frost event was. This is a month after the event, showing a black spruce branch, and you can see just a few needles retained at the ends. Normally these guys would retain foliage for 7 or 10 years. And it's only retaining a little bit from the current year, or the previous year, and you can see here, these are the buds that would then flush and put out new foliage. And these guys are still alive, they are recovering, but if this happens very frequently, it's going to be pretty hard for them to tolerate, I think. Okay, so we're tracking phenological responses in this warming experiment using the PhenoCam approach. We're seeing that warmer temperatures are extending the growing season at both ends in this boreal black spruce bog. So far, there's little or no evidence for photoperiod control of phenology because the phenological response to temperature appears to be quite linear. We've also seen how in the warmest plots, these warming treatments are causing early loss of winter hardiness, and then that's got the potential to lead to severe frost damage. And this is consistent with predictions that have been in the literature that warmer temperatures in the future will lead to actually frost damage becoming more common, which is somewhat paradoxical. Then in the long term, we think that we may expect to see additional indirect effects of temperature on phenology as there's the potential for these warming treatments ultimately to drive changes in species composition within the different chambers. So just to wrap up here, I want to briefly talk about the PhenoCam Dataset version 1. This is 125 sites of PhenoCam sites, consisting of 750 site years of data which have been fully processed and quality controlled. The data and the imagery have all been posted sort of as a permanent long-term archive to the Oak Ridge National Lab DAC. We've made the data set publicly available under a Creative Commons public domain dedication, and the whole data set is fully documented in a publication in the journal Scientific Data, shown here, which just came out a few months ago. And just to wrap up, with PhenoCam, we're using network digital cameras and a common configuration and deployment protocol to track vegetation phenology in ecosystems across North America and even around the world. The data and imagery are all publicly available in near real time through the project webpage. Again, that's the URL there. And we're then using these data to develop new models and make predictions about how, through shifts in phenology, climate change is going to influence ecosystem processes related to carbon and water. So thanks very much, and if you've got questions, I'll be happy to talk about any of this stuff. So thank you.
Yeah, over the past several decades, there's been a shift in species composition in those forests.
Okay.
With no change in land use or anything, just increase in eastern Red Sea.
Okay, really? Okay.
Yeah, and so you're not replacing, but you're just increasing the amount of evergreen in the deciduous forest. And I was wondering how you pick that up with a non-species specific model. And it's not just a response to climate change, it's a response to change in disturbance regime because of lack of fire.
Lack of fire, yeah. Well, that is interesting because the land cover classification, it may be considering as deciduous forests that over time have an increasing component, as you say, and so yeah, that could be problematic. But generally, what we see is that a in these mixed species forests, having some evergreen cover doesn't really change the phenological signal that much, because although I showed that evergreen forests do have some seasonality, it's sort of like this, and the deciduous forests are like that. So as long as the deciduous component is, you know, fairly strong, then that signal overwhelms any evergreen signal, and so what we're still seeing is mostly a deciduous signal. But that certainly could, why the NPN model is doing very poorly here, but I guess I might expect both models to be doing poorly if there was really sort of a contamination thing. I don't know. I don't have a great explanation for that, but this modeling is not taking into account those